So what topic are we going to tackle today, do you say? Well, today's topic is going to be the conservation of momentum, which you guys did some simulations on Wednesday, and today we're going to try to apply it in class in terms of problem solving. So the one big issue, not that there's only one big issue with COVID, this is probably the least of them. But one thing that happened as a result of this year's hybrid schedule is that I found myself falling behind in terms of the pacing for this year. So I had to shove in this little chapter before the end of the semester. One issue with that is that physics usually progresses in a natural order, and there's a unit, a rather large section on work and energy that normally comes before this. So there's some ideas that should be incorporated into this chapter that were not, that I'm going to have to come back and clean up the pieces later. So just, that's neither here nor there, but realize that I've got to circle back to this once we start again in January, once we start talking about momentum and energy. So just kind of be aware of that. So what are we going to be looking at? So the law of conservation of momentum says this, okay? If I have some initial momentum of the system, that is going to equal the final momentum of the system. So the momentum at time zero, or we've been oftentimes calling this the initial momentum, that is going to equal the final momentum, especially if I've got a system of bodies that are going to interact with one another. So one way you can interact is to collide with an object, and instead of showing a simulation, we will kind of illustrate this, but basically things are going to bounce off each other, and you saw that with your simulations. And we're going to consider these to be ideal collisions where there's no energy loss. Now, in reality, most stuff falls in between this type of collision and the other one. So in an elastic collision, the objects are going to bounce off each other, and if that's the case, I have two sets of objects. I've got object 1 and object 2, object 1 and object 2. This would be the total initial momentum, the addition of those two together. So we'll call that P initial, and this is going to be the P final. It's both of these two momenta together. So that is an elastic collision. And in an elastic collision, both momentum and, as we're going to find out, kinetic energy are conserved. Sorry guys, I got interrupted by another class that was dialing in while I was recording this. So an inelastic collision is when things stick together, okay? And in this case, again, we won't show a simulation here. You did some simulations the other day that relate to this. I start out with two objects, and I end up with one with a shared velocity. Okay, again, momentum is conserved, but in this case, kinetic energy is not conserved, and we'll talk about that in January. But momentum is still conserved. It's a law of conservation of momentum. The reason why energy is lost is because the rest of the energy is converted into heat and sound in an inelastic collision. Now we can also have explosions where things are going to start together and move apart. It's basically this in reverse. But either way, the whole concept is that momentum is conserved. So I'm going to show, what I'm going to have you guys do here is pause this video and look at the other screencast where I'm going to illustrate some of these concepts, and then come on back to this, this screencast when you're done with that. Okay? So let's look at a demonstration problem. I've got a 70 kilogram man and a 55 kilogram woman holding a 2.5 kilogram purse. So this woman's holding a 2.5 kilogram purse. They face each other on the ice. The woman pushed the man back for 0.5 seconds. So maybe it's a blind date gone wrong. I don't know, but she's pushing him back. Maybe it's in fun. Maybe it's in anger. But his speed is going to be 1.5 meters per second. We can ask what force she applied and what is her speed. So we've got kind of two questions at play here. So one of these is that the initial momentum of this system, we'll call it PI, is 0. They're both together, but there's no motion, so there's no velocity. There's no momentum. They're standing together on the ice. The mass of this first person is 70 kilograms. Mass of the second person is actually going to be 57.5 kilograms because they're holding a purse. It's a system. First thing we're going to look for is the force. So this is an old momentum issue. The force is going to be, the change in the force is going to be, or the change in momentum equals the impulse here. So it's the mass times velocity is going to be what my change in momentum is here. My change in momentum equals force times time. So if that's the case, force times time equals my change in momentum, or the momentum that this person has. So the man, mass of 70 kilograms, now he's moving at 1.50 meters per second, and you divide that by the time that he was in contact with the woman, and so we can solve that way. That's going to be how we solve that answer. Second part is, how fast is the woman traveling? So in the second part of the problem, we know that the momentum afterwards is going to equal 0 because it started at 0. So in this case, the mass of the man times the velocity of the man afterwards is going to equal the mass of the woman plus the purse times the velocity of the woman plus purse afterwards. So you set it up, you're going to isolate, you're going to take the, you're going to set these equal to each other, and what's going to happen here is that one of these is going to be a negative value. You get to choose which one, but we can subtract that over there. And so the velocity of the woman plus the purse is going to be, I'm simply going to take this and divide it by the mass of the woman plus the purse over here. So you can see how this jump is happening. I want to isolate this by itself. So that is going to be right there. And that is going to be our answer. We could plug in our numbers. We could plug in 70 for the man. We could plug in 1.50 meters per second. We could plug in 57.5 kilograms for this mass. And we'll end up with what the velocity of the woman is. So these problems really aren't that hard mathematically. They're more bean counting exercises to make sure that you understand the concept. Okay? So here's another issue, another problem. This time we have two objects that are going to collide, but now it's going to be an inelastic collision because they become entangled here. They are going to stick together. Okay? And so they're going to become entangled. We've got a truck moving with a velocity of 18 meters per second, mass of 1,800 kilograms. It collides with a smaller car at a slower speed. They're going to stick together. So the momentum of the truck and the momentum of the car are going to equal the momentum together. So the momentum together is the mass of the truck plus the mass of the car. They're going to act as a single unit since they're entangled, times the final velocity. The final velocity then simply ends up equaling the momentum of the truck plus the momentum of the car divided by the mass of the truck plus the mass of the car. Now you could flesh this out and say, hey, this is initially the mass of the truck, velocity of the truck, plus the mass of the car, velocity of the car. But this is going to give us our final velocity of the two objects together as one system. So, based upon that, you're trying to conserve momentum. This is what I'd like you to tackle for next class. Okay? Please let me know if you've got questions. These problems shouldn't be that challenging for you. They should be a nice little kind of easing off on the gas a little bit compared to where we've been. But if you have some issues, let me know. I'm more than happy to help you out.